All right, so this video is going to be your introduction into the next section here called approximating areas under curves. And, the title of it kind of gives away the whole idea, but that's okay because it's a little bit to consume. And you're almost definitely not going to get it on the first time through. So, be prepared to reread this or, re-watch this video. Keep in mind as we're going through this, that this is a very easy concept. And then really what happens is that the notation gets so, I don't know the right word, dramatic or whatever, that it kind of gets in the way of the idea that this isn't really that big of a deal what we're talking about. But the notation is very serious stuff. What we're talking about here and what this first paragraph is saying is that so far we start with a function and we spend all this time doing derivatives. And we always keep coming back to, well, what is a derivative? Well, it's the slope of a tangent line. And so this is like the geometric idea of a derivative. And so what the book's saying is like, well, then what's the, if we're talking about an indefinite integral or antiderivative, what's its corresponding geometric idea? And so we're going to answer that right away here. And notice off to the side, they're telling you, hey, by the way, remember what we're talking about from earlier, is that displacement of an object moving down a line. And remember, we're only going in two dimensions. It's either left and right or up and down. Is the difference between its initial and its final position. Okay, that's displacement. If the velocity of an object is positive, its displacement equals the distance traveled. And so what we're going to do is start off only thinking of things in the positive direction, so above the x-axis. So we're only dealing with the first quadrant. Eventually we'll move on to the first and fourth quadrant. But the idea of velocity and position and acceleration are something very nice for us to grasp. And again, it's the easiest thing for us to think about, but this applies to any function that represents any kind of situation. So what we're going to start with is this idea. And so what I'm going to do when I'm going through this is this first little intro example, I'm going to do it exactly like the book. And then I'm going to switch off, and I'll explain to that why I'm going to switch off, to do separate examples when we're going through the actual process here. But first, let's, if you read this, they're saying, you're traveling down a highway, a straight highway, at 60 miles an hour, and you're going 60 miles an hour the whole time. And so let's take a look at what the velocity graph would look like. Let me get to a little bit more room here. And so then up here at 60, we're just cruising, right? Our velocity is positive, but it's constant. And in there, they're saying that we're going to measure this situation in over 2 hours. Okay, so this would be 1 hour, and then finally 2 hours. And so let's get our. I'm gonna label the axes here. So this is time in hours, and then remember this is a velocity graph. So our y-axis is actually miles per hour. Okay, and so the reason we're starting with this is because everyone knows, with this formula, distance equals rate times time, or displacement equals rate times time, that if we're cruising at the same speed, if you're cruising down the highway at 60 miles an hour, you set your cruise control, and you go for 2 hours, we all know that your distance that you've traveled is going to be 120 miles. Okay, so let's take a look at the graph and what we're talking about here. And pay attention to the units that we're using, right? We started with miles per hour and time, and then once we multiply them together, we have miles. So, and I'm going to come back to that here in a second. So if you think about what it's doing on the graph, the same situation, what we're saying is at 2 here, like if I drew a line straight up at 2, we'd make this rectangle. And this area right here of this rectangle we could find by just multiplying the length and the width. And it just so happens that since our length, in this case we'll say 60 miles an hour, and the time 2 happen to be the exact same formula as our distance equals rate times time. And so what we would have is the area equaling 60 miles per hour times 2 hours. Okay, and so then when we multiply this together, right, the hours cancel, and we're left with that 120 miles. So, and now, now think about how, if we're going from our position, if we're going from our position function to our velocity function, right, position would be our miles, and then we go to velocity, and we would be at miles per hour. If we're going in the other direction, starting at miles per hour and going to miles, we've actually just, the units are telling us that we've just taken an antiderivative. And so then that's the relationship right there. And that's basically the whole thing, is that all we're doing when we're taking an antiderivative or an indefinite integral, all we're doing really is finding all this area underneath the curve. Okay, and so what makes this more of a challenge is that this area under the curve, it's not always going to be just a straight line. And so these next couple examples, we're going to kind of advance off of this idea a little bit. But notice that what we're talking about right now is a rectangle. Rectangles are super easy to find the area of. You just do the length times the width. Okay, so keep that in mind as we proceed here. Okay, so I'm really going to, I'm going off of the book at this point for the next several ideas. Okay, but the idea is going to be the same. I'm going to, first let's just make sure that we get, let me get this out of the way here. This is the function, right? We're going to start really basic. So instead of having a constant, we're going to mess with just a linear function here. And we are thinking about the antiderivative of it, or the indefinite integral of it. And so again, what that means is we're really finding the area underneath this curve. And we're going to go from 0 to 8, and that's as far as we're going to go. Now, we know what the area under this curve is. And so then the area under this curve, right, we can find this. This is just a triangle. So we're going to here, right? So that we're going all the way here. So we can actually find the area of this, just because it's a triangle, by 1/2 base times height. And so in this case, this would be 1/2 times 8 times 8. Or 8 squared. So then that would be 32. Okay, and so, if you think about, like, what is the antiderivative of our function that we're talking about, right? You go up 1 and then divide by that, right? 1/2 8 squared, right? 1/2 8 squared. Okay, so that's the relationship that we're looking at. So we actually don't need to go through the process that I'm going through, but it's an easy concept to understand when it's just a straight line here. So the idea is that we're going to assume that we don't actually know the area to begin with, and we want to approximate this area. So what we're going to do is to break this interval down here, we're going to break this into what they call subintervals. And how many subintervals are we going to break this down into? Well, it depends on what we're being asked. We're going to start with only breaking it into 2 subintervals. Okay? And what we're going to do is construct rectangles that represent an approximation of the area under this curve. Okay? So right now we have one giant interval, 0 to 8. We're going to break it down into 2 subintervals. So our first interval will be from 0 to 4, and then the next one from 4 to 8. So what I'm going to say is, again, we're trying to approximate this. So what I'm going to say is, I'm going to draw a rectangle like this. That's my first subinterval. And then my next subinterval I'm going to draw like this. And I'm going to say, that's a relatively, it's not a super accurate, but that's kind of an estimate of what the area would be. And it's something that I can handle. So for instance, I can say, well, this first rectangle is a 2 by 2. Okay, so then we would say the area of this rectangle and then the area of this second rectangle, right, is again 2 by, but in this case, 6, 2 by 6. And so then if we added those up, we'd have a total area under the curve being 16. Okay, and that's not super accurate, but, right, it's kind of getting us a little bit. So instead of doing 2 subintervals, let's take a look at maybe making these intervals a little bit smaller. So let's try to do 4 subintervals. So if we're doing 4 subintervals, we're going to look like that. And so again, I'm going to draw my rectangle, and I'm going through basically my height is becoming the midpoint of my rectangle. Okay, and so this is getting us a little bit more accurate. Now, I want to point out that since we started with our overall interval from 0 to 8, and we've split those into 4 subintervals, 4 little sections, then what we can say is that our width, if we can call it width, is equal to 2 now. And so what that is, what we could also call that is just the change in x. So the change in our x value on all of these subintervals is now 2, okay? And this is going to be part of our notation as we move forward. So now let's check the area again. We know that the width on all of these now is 2. And so now all we're taking a look at is the height. So the height on this first one would be 1. The height on the second one would be 3. And right, how am I getting that? Right, I'm just, basically I'm counting up right now. Then by 5, and then by 7. Now I'm counting up, but just to make sure that we're all on the same page here, we are trying to find the area of all these rectangles, and we need a length and a width. So if we call our width this change in x, then right now, it's easier, just counting up to get to the height. But what you're really doing is evaluating that function at a certain point on your rectangle, in this case the midpoint. So like if I'm looking at this one, then I just went to the midpoint, which is 3, and evaluated this function at 3. And that gave us the height on all those. So that's going to be an important idea here going forward also. Now let's see how we did with this estimated area. Again, we know that it's 32. So let's see what happens when we shrunk it down just a little bit. So we have a 2 plus a 6 plus a 10 plus 14. And sure enough, we've already gotten to the right area. Okay, so just by shrinking up our subinterval just a little bit, we were able to get an accurate estimate. And it's not even an estimate, it's actually what it is. So let's take a look at a little bit more of a complicated situation. So here's a new function. This is x squared. And we're looking at it only on the interval from 0 to 8. And now keep in mind what we're trying to do. We're trying to find the area under this curve, or at least estimate it right now. And how are we doing that? Well, we are making little rectangles, finding their areas, and then adding them up. And that's our idea. Now this is obviously going to be a little more challenging because we don't have this constant rate of change anymore. Right now we're up into the bigger kinds of functions. So let's just take a look at what would happen if we wanted to go from the full 8, which would, rectangle, if we made our first rectangle here, right, this would be not even close to accurate, right? This whole area up here, it doesn't count. So let's start by looking at what if our subinterval, what if we change our subinterval and have 2 of them? And so that would be right here. So then what we'd be saying is our change in our x value would be 4. So again, I'm just going to go up to the midpoint. I'm going to use the midpoint here and draw a couple rectangles. Okay, so our, going from, an interval of 0 to 8, breaking it into 2 equal subintervals with a width of 4, we don't get really that accurate of an estimation, right? We have all this area here, but that doesn't correspond to that. I mean, just like looking at your eyes, this side looks bigger, and then this side looks bigger than that. So this isn't going to be a super accurate one. That was when we go to 2 subintervals. So let's take a look at breaking it down into even more subintervals. All right, so let's try 4 subintervals. I marked them out already. And so then now what we're saying is our width now is 2. Our change in x is 2. I'm going to set it up the same way. I'm going to draw little rectangles. This first one's going to be hard for me. Not as good as you guys are going to get. All right, here's another. Okay, so again, we're trying to estimate this area under the curve. We're getting better. It's getting closer, more accurate to what it really would be, but we're still off. Again, it's still pretty easy to see that these areas are not equal. So let's go to another step. Let's increase our subintervals. All right, so now we're taking our original interval from 0 to 8. We're going to break it down into 8 subintervals. And that means that our change in x has now become 1. Okay, and so that would be our width. And so that one's hard to draw. That one's hard to draw. But I think you can see that we are getting more accurate. And now I keep going through the midpoint, and we're going to talk about that idea here real briefly, or very soon. But I think what you would see is that in fact, it's getting more accurate. And if we could keep just shrinking up these subintervals, or making more and more of them, making our change in x even smaller, we would become more and more accurate as we increase the subintervals. So let's take a look at what our area would be at this point if we had this many subintervals. So remember, all we're doing is the width, which we'll call change in x, times the height. Now this isn't really x, but I'm just using this as a function right now. Okay, so the notation is going to be a little bit different. But remember, we're just doing an area of a rectangle. That's all we're doing. So it's just width times height, and then adding all these things up. Okay, so the notation I'm using right now isn't exactly what we're going to keep. But what we can say is that all of our changes in x, so we're going to have 8 of them, it's going to be 1 times something, plus 1 times something, plus 1 times something. Right, we're going to keep going. I'm going to start filling out those somethings here in a second, but our widths are all going to be the same. Okay, so what is our heights? Well, remember that I'm using the midpoint of the subintervals. Okay, and so the height is going to be using 1/2, and then 1.5, and then 2.5, and then 3.5. That rectangle isn't very good, right? But so you see what I'm saying? So then really what we're doing is saying, okay, our width is 1, then our height would be f of 1/2. And then our height on the next rectangle would be f of 3/2. And then f of 5/2. And I'm trying to make this not sloppy, but so that was our third rectangle, right? So, right, that represents, we're right here right now. Okay, plus the width times the height, plus the width times the height, plus the width times the height. Right, 1, 2, 3, 4, 5, 6. Right, we're on our 6th one. We need 2 more. Plus our width times our height. Plus our width, 1 more, right, times our height. Okay, so all we did, right, hopefully you can still see that okay. Right, 1, 2, 3, 4, 5, 6, 7, 8 rectangles. All of them have a width of 1. That was our change in x. That had to do with our subinterval decision. And then we found the height. All these f of fractions here, these are the height. Where did these fractions come from? Well, these were the midpoint of our subinterval. 0.5. 1.5, 2.5, 3.5, 4.5, 5.5, 6.5, 7.5. Right, and we plug all those in. What are we plugging those into? Well, remember, our function is x squared. So when we evaluate this all out, what we do is our area with 8 subintervals is going to be 170. Okay. So now, this is page 351, right? They're showing you basically what we just did here. Now, I didn't add up these areas, but we did get to 8, right? With a length of a subinterval of 1, we got to 170. And then they're saying, like, look, if we keep making these subintervals smaller and smaller, in fact, we'll go to the subinterval size of 64, it sure looks like we're going to a number here. It looks like we're approaching a number here. In fact, they're saying that it looks like it's approaching 170.7. And now, if you think back, when we start talking in terms of what is this approaching, what is this y value approaching, then the first thing that should be popping into your head is limits. And that's where we're going to end up going. Now, we're not going there yet, but that is what we're heading toward. Okay, so as we keep going through this, understand that you just learned everything that's going on. Okay, there's nothing that we're about to, or that I'm about to go over that I didn't just go over. It's now entering into, do you understand what the notation is saying? Okay, and again, this is kind of intimidating. So, but remember, all we're doing is making little rectangles, or rather, rectangles of a small width, finding its height, multiplying them together, and then adding them all up. So we find that however many subintervals we want, that's how many rectangles we're going to find the area of, and then we're going to just add them all together. That's all that we're doing. Okay, so let's take a look at what they're saying here. Let's develop a method of approximating areas under curves. Consider a function f that is continuous and non-negative on an interval a to b. Again, we're going to get to the negative ones eventually, but not now. The goal is to approximate the area of the region R bounded by the graph of f and the x-axis. Okay, we're always bounded by the x-axis when we do this. From a to b. So we begin by dividing the interval a to b into n subintervals of equal length. Okay, and that's what we were doing before. And so now they're giving us this here. And they're just naming the size of the subinterval. From this point to this point. That's a new subinterval. This point to this point, this point to this point. Okay, and it keeps going. Okay, so this is just a notation of the beginning of your subinterval to the end of the subinterval, just like a to b. These are all just little subintervals. And notice that they end at n. And what is n? N is the number of subintervals. And now they say, where a, that's what I just said. A equals x of 0, x sub 0, and b equals x sub n. So then we can find the length of each subinterval, and we're going to call it the change of x, just like we were before, by finding this little formula. We take the original endpoint, subtract the original beginning point, and then divide it by however many subintervals we need. That's what we were doing before. Why is this number important? This is going to be the width of every single rectangle that we use. And so then they kind of illustrate this down here. So super important stuff. Okay, now let's see what they're saying here. So we need to know this definition. Let's read this carefully. So we got this regular partition. This is the definition of a regular partition. Suppose we have this interval from a to b. It's closed. And we decide that we want n subintervals, just like we were deciding before. Maybe we want 2, maybe we want 4, maybe we want 8. We're making that decision, or someone's making that decision for us. Okay, so we're going to first find our change in x, right, width. This is width, by taking our endpoint, subtracting them, and dividing by however many subintervals we want. Okay, these endpoints, right, that's an endpoint, that's an endpoint. That's an endpoint, that's an endpoint. We're going to call those grid points. And they create a regular partition of the interval a to b. Okay, and here's another one of these things. In general, the kth grid point, okay, any of them, wherever you want to go, the kth grid point. Remember, grid point is an endpoint, one of these. The kth one is found by this x sub k. This is going to be an important one. This is x sub k right here. Okay, and what is x sub k? Well, remember, this is a grid point, so it has to be one of our endpoints of our subintervals. You know, before we were going like from 0 to 1, to 1 to 2, to 2 to 3. Okay, and we can find that grid point if we start at our first point, we start here, and then we add our width times however far down you're asking me to go. Right? Don't ask me to go past the number of subintervals, because then we're outside of our original, you know, that put us outside of this. So where is this one? Well, you tell me which one you want to look for. Don't pick something bigger than n. Don't pick something bigger than the subinterval. And then I'm going to say, okay, well, let me start at our starting point. Let me take whichever one you're looking for and multiply it by our width and add that together, and then that's where we're going to end up. Okay, so let's take a look at that here for a second. So let's look at that by looking at the graph of x squared again. Okay, and so let's go back to the idea that we're looking at. Let's just go to the idea of 4 subintervals. So if we're doing 4 subintervals, well, let's put all of this into practice, right? So let's see what our change in x will be if we're going from 0 to 8, and I want 4 subintervals. That means the change in x is going to be 2. Okay, so that's that first part of the definition. You have to find that first whenever you're doing this. Okay, and so let's list out our subintervals using the grid points. So that would be 0 to 2, 2 to 4, 4 to 6, and then 6 to 8. Okay, so all we're doing, I'm just trying to apply this definition the way you're going to need to, right? I'm telling you that we're using x squared, and our interval is 0 to 8. And I want to break this down. I just decided to do 4, mostly because I can't fit any more on here comfortably. So then I did the endpoints, subtracted the endpoints and divided them by however many subintervals I decided. That gave me the width of every single rectangle, and that's what this is representing. So then our grid points are 0 and 2, 2, 4, 4, 6, 6, 8. So now let's say you're sitting there watching this and you're just like, okay, I want to know then, you know, we're looking at this part now. I want to know actually where the third grid point is. Okay, so again, you can't pick a number bigger than this. It wouldn't make any sense. Okay, so where is the third grid point? Okay, so let's look at what they're saying here again with this x sub k. Right, they're saying start at your starting point and add k times your width. Okay, so then what we're doing right now in our made-up situation is saying, I want to know where that third grid point is. And so then I'm starting at A, and A in our case is 0. And I'm adding 3 times the width. Well, the width we just decided was 2. So then the third grid point is actually 6. And let's take a look at that. Here's the first grid point, the second grid point. The notation starts with x sub 0. So that would be x sub 0. This would be x sub 1, x sub 2, x sub 3. And then we could finally get to x sub 4. Okay, so you notice that they're sharing some of these. Okay, so x sub 0, x sub 1, x sub 1, x sub 2, x sub 2, x sub 3. x sub 3, x sub 4. So where is that third one? It's at 6. Now, you could be saying like, well, I could have just counted those out, as long as you start with x sub 0, right? Right. So you can say, I could have just counted them out if I started correctly. Like, right, I wanted to get that in there. So, right, but remember, we're not really super accurate. We're going to start slimming these things up a whole bunch more. In fact, we're going to slice them into an infinite amount of subintervals. So, yeah, you can count these, but if we get further along, so for instance, like on the example they went to, the previous example, the book went to 64 subintervals, counting 64 might be a kind of a pain. Okay, so then we can just find it with this formula. So again, another important formula here. So now when we take a look at this, right, what they're saying is, right, we're going to get a little bit more deeper into this notation. Okay, so now we're saying, let's go to that interval, whatever interval you want. It doesn't matter. I just showed you how we got there. We can name it. Okay, we're going to choose any point in that rectangle on this little subinterval, and then we're going to just denote it by whatever subinterval we're looking at. We're going to put a star on there representing, hey, this is the point we're using. And what we were using before was always the midpoint. Okay, but we can pick any one, right? That height isn't going to change on the rectangle. And we're going to build our rectangle with that height, right? Remember, this is how we're denoting the height. We're going to plug any point on our subinterval and plug that into our function to get the height. We already found, right, it's up there a little bit, we already found the width. And so now we have this height and base, okay? So I'm going to just say it again, and it's got to sink in. Nothing hard. We got a width that we found by deciding how many subintervals we wanted, right? And we're multiplying it by a height, and that height is being generated by picking any point in that subinterval, plugging it into our function to get the height. Okay, and then we're going to just do that to every single rectangle that we have. We're going to find all those areas, we're going to add them all up, and that's going to be our approximation of our area under the curve. And it's called a Riemann sum. Okay? Now, and you can read a little pull-out about Riemann over there. Okay? Now, this x sub k, x star sub k, however you want to say it, can be any point on the rectangle. But let's get real. Like, you're not going to just randomly pick numbers, right? Let's keep it easy. We're either going to pick the left-hand side of the rectangle, the right-hand side of the rectangle, or the midpoint of the rectangle. That's all we're going to pick. Those are our three options. Okay, so I'm going to go through all three versions of the Riemann sum. We're going to do the left Riemann sum, the right Riemann sum, and the midpoint Riemann sum. So I'm going to graph each of them and show what we would be using for each of these new notation situations. Okay, so I'm going to graph each of them first. Then I'm going to go back and talk about like what those areas would end up being. So the first thing to keep in mind is that we're still back on the x squared. The y equals x squared, f of x equals x squared. So let me put that up here. Oops, sorry. Okay, and for all of them, I want to have the same amount of subintervals, right? We're on, right, just to keep everything the same, we're on this interval. This is our big interval. Okay, and I'm going to make it so that all of them are, every one of these is left, right, and midpoint. We're all going to have a number, the subintervals, right? We're calling that n now. Let's do all of them 4. Okay, and that's just so visually we can see it a little bit better. Okay, so then let's first decide what our width of all of our rectangles are going to be. And that's going to be denoted by the change in x. Okay, so we won't do this every time. But again, or for all three of them, we're going to just use this. So it's 8, right? The interval length divided by the subintervals, that gives us our length. So the first one we're going to do is, let's Let's do the right one first, even though I said left a second ago, so you can see it, and then the left one kind of looks a little bit different. So I think it's easier to start with this. So here's our subintervals, and we're going to do the right Riemann sum. Okay? So then visually, what that means is that the height that we want to use is going to be on the right corner of each rectangle. So then I'm going to go up to here and over. I'm going to go up to here and over. Right? This is the right. Oops. Riemann sum. Okay? So let's go to the left Riemann sum. This will be the left one. Our change in x is the same. But now the left Riemann sum is saying, let's get our height from the left-hand side of the Riemann sum. And so, right, this one's a little bit weird because our left-hand side would be 0. And so our first rectangle essentially doesn't exist. Okay, and so here's our next one. Here's our third rectangle. And now our fourth rectangle. All right, now let's do the midpoint Riemann sum. And here's our subintervals that we decided on. So this one's hard to draw. Oh, I did pretty good. Right, so there's our first one. Second one, right, we're using the height of our rectangle is now the midpoint of our interval. Okay, and this is what we really started on doing, or started with, rather. Okay, so that's visually what these are. When we talk about the midpoint Riemann sum, we're talking about using the midpoint of our subinterval as our height. When we talk about the left Riemann sum, we're using the left-hand grid point of for our height. When we talk about the right Riemann sum, we're using the right grid point of each subinterval for our height. So let's take a look at those subintervals. So right, we decided to go from 0 to 4. Right, and we're talking about these. Right, there's our 4 subintervals. And so for every single one that we just drew, left, right, midpoint, our subintervals are exactly the same. They are 0 to 2, 2 to 4, okay? Remember what we're doing. We are trying to find the area of each of these rectangles. What do we need for that? We need a width and a height. What is our width? Let's start with that. All of our widths on all 3 of these versions are going to be the same. That's determined by your original interval and how many subintervals you want. We've already decided that we're going to have a width of 2 on every single one. So then all we're doing right? We're determining the height. And what is the height again? Well, the height in our notation, if I can do it, is going to be this. And what is this? Well, it depends on if we're talking about the left Riemann sum, the right Riemann sum, or the midpoint Riemann sum. It all depends. But it's going to yield us a height when we plug that x value in. So we started with the right, so let's take a look at the right. Okay? The height of the first subinterval is 2, it was f of 2. The height of the second rectangle is f of 4. The height of the third one is f of 6, and then finally f of 8. So notice that those are the right grid point on each of our interval. So for the right Riemann sum on this, we're saying that it's going to be, right, let's do it this way. All of our rectangles are going to be this. Well, let me stay consistent with the book here, right? It's the height of whatever value we're deciding to look at on our subinterval times the width. Okay, so all 4 of these are going to be found like this. Remember, the right one means we're using the right grid point. So then we're going to say that it's going to be 2 for our width. Well, I'm going to stay consistent here. Right, so then our height would be, all right, so then how are we finding this height? Right, this is the right Riemann sum, so then it's going to be f of 2 times the width. Why? Because we're using the right-hand grid point. Plus f of 4 times the height. Plus f of 6 times the height. Plus f of 8 times the height, right? We just needed the height of, times the width. Sorry, if I was saying, the 2's are the width. Sorry, if I said that wrong, right? We're just using the right-hand grid point. That's where it all comes from, right? Each one of these, right? There's our first one, there's our second one, there's our third one, there's our fourth one. They're all on the right-hand side. They're the right-hand side grid point, okay? So remember, we're just using x squared here. So then really this is 4 times 2 plus 16 times 2 plus 36 times 2 plus 64 times 2. And all that equals, let's see, 8 plus 32 plus 72 plus 128. Add all those up, and we get 240. All right, so that's the right one. So the process is the same for the left one. The difference being, and what the similar thing is that our change in x is still going to be 2. The difference is that we're going to use, instead of up here where we're using the right-hand height, we're going to use the left-hand height now, okay? And so the process will be the same, though. We're just going to find the height at each of those points. So again, on the left one, we're going to do an f of 0, and f of 2, and f of 4, and f of 6. Okay, so then we're saying f of 0 times the width plus the height of the second one times the width plus the height of the third one times the width plus the height of the fourth one times the width. Okay, so then that's going to be 0 plus 4 times 2 plus 16 times 2 plus 36 times 2. So then that's going to be 8 and 32 and 72. Okay, and so then 41, that'd be 80, 112, is that right? Okay, so using the left Riemann sum, we're way different than when we were using the right one. But if you look up here, I mean, I think you would agree that, you know, the left one is way underestimate, right? Where the right one is an overestimate. Okay, so then the midpoint is going to be a little more accurate. But what we're going to have to do is take the midpoint of all of these intervals. Okay, so then the value that we're plugging into our function to get the height is going to be 1, 3, 5, and 7. But we're going to treat it the same way. And our width is identical. Okay, so our width is still going to be 2. And now we're going to do the height of the midpoint plus the height of the, what is it? Right? Plus the height of the midpoint plus the height of the midpoint, of course, times the width on all these, plus the height of the midpoint. Okay, so then this is going to be 1 times 2 plus 9 times 2 plus 25 times 2 plus 49 times 2. So then 2 plus 18 plus 50 plus 98. And so then using the midpoint Riemann sum, get that it's 168. Okay? So that's all you're doing. There's nothing else to this except to get over the notation, which you're going to have to take a look at. So I just did everything with up to page 355. Now they used a different function. They were using sine. And I thought that using sine is, you know, you're worried about trig, and so it's unnecessary for the first exposure. So that's why I used x squared. But you can read through and it'll be exactly kind of what I'm talking about here. And like I said, it's really easy. Here's what you're doing. You're taking a big interval, making it into equal length small interval, drawing a bunch of rectangles, and depending if you're doing the left, the right, or the midpoint, figuring out your height, figuring out your width, finding a bunch of areas, and then adding them all up. So at this point, you should be able to handle, starting on number 9, you should be able to get to 33 odd. Okay, and it's going to get monotonous, but you know, that's good. Once you feel comfortable with it, right, then that means that you're kind of understanding what's going on. So definitely give these a try. Definitely get some questions. Definitely try to work through those notations because that's going to be very, very important.